I actually prepared you something to just entertain you and also to send you a message. And this is actually a speech given by Steve Jobs. Maybe you have heard of it. In 2005, at the ceremony of graduation at Stanford University. And this is a very nice one. And we will not listen the full of it. I will just play a third of it. And there's a nice, interesting story over there. And hopefully you could enjoy it. Let me ask you, do you hear well?
Yes, for the moment is good.
Awesome. Thank you.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
Thank you. I'm honored to be with you today for your commencement from one of the finest universities in the world. Truth be told, I never graduated from college, and this is the closest I've ever gotten to a college graduation. Today, I want to tell you 3 stories from my life. That's it. No big deal. Just 3 stories. The first story is about connecting the dots. I dropped out of Reed College after the first 6 months, but then stayed around as a drop-in for another 18 months or so before I really quit. So why'd I drop out? It started before I was born. My biological mother was a young, unwed graduate student, and she decided to put me up for adoption. She felt very strongly that I should be adopted by college graduates, so everything was all set for me to be adopted at birth by a lawyer and his wife. Except that when I popped out, they decided at the last minute that they really wanted a girl. So my parents, who were on a waiting list, got a call in the middle of the night asking, "We've got an unexpected baby boy. Do you want him?" They said, "Of course." My biological mother found out later that my mother had never graduated from college and that my father had never graduated from high school. She refused to sign the final adoption papers. She only relented a few months later when my parents promised that I would go to college. This was the start in my life. And 17 years later, I did go to college. But I naively chose a college that was almost as expensive as Stanford. And all of my working class parents' savings were being spent on my college tuition. After 6 months, I couldn't see the value in it. I had no idea what I wanted to do with my life, and no idea how college was going to help me figure it out. And here I was, spending all of the money my parents had saved their entire life. So I decided to drop out and trust that it would all work out okay. It was pretty scary at the time, but looking back, it was one of the best decisions I ever made. The minute I dropped out, I could stop taking the required classes that didn't interest me and begin dropping in on the ones that looked far more interesting. It wasn't all romantic. I didn't have a dorm room, so I slept on the floor in friends' rooms. I returned Coke bottles for the 5-cent deposits to buy food with. And I would walk the 7 miles across town every Sunday night to get one good meal a week at the Hare Krishna temple. I loved it. And much of what I stumbled into by following my curiosity and intuition turned out to be priceless later on. Let me give you one example. Reed College at that time offered perhaps the best calligraphy instruction in the country. Throughout the campus, every poster, every label on every drawer was beautifully hand calligraphed. Because I had dropped out and didn't have to take the normal classes, I decided to take a calligraphy class to learn how to do this. I learned about serif and sans serif typefaces, about varying the amount of space between different letter combinations, about what makes great typography great. It was beautiful, historical, artistically subtle in a way that science can't capture, and I found it fascinating. None of this had even a hope of any practical application in my life. But 10 years later, when we were designing the first Macintosh computer, it all came back to me. And we designed it all into the Mac. It was the first computer with beautiful typography. If I had never dropped in on that single course in college, the Mac would have never had multiple typefaces or proportionally spaced fonts. And since Windows just copied the Mac, it's likely that no personal computer would have them. If I had never dropped out, I would have never dropped in on that calligraphy class, and personal computers might not have the wonderful typography that they do. Of course, it was impossible to connect the dots looking forward when I was in college, but it was very, very clear looking backwards 10 years later. Again, you can't connect the dots looking forward. You can only connect them looking backwards. So you have to trust that the dots will somehow connect in your future. You have to trust in something, your gut, destiny, life, karma, whatever, because believing that the dots will connect down the road will give you the confidence to follow your heart even when it leads you off the well-worn path, and that will make all the difference.
All right, that's the part I would like to play for you. And now let's get back to the lecture. All right, so that was the part called connecting the dots. Actually, you might sense something differently because that's a very nice story to be told, actually. And reflecting that in our lecture, I would say, now it is also the time for us to connect our dots here. And probably you have been already getting familiar with this because we're doing at least not at the very beginning, but already in the middle. But now we're completely at the end. So as Steve said, it is easy to connect dots while you just look backwards. And it is hard to do it at the beginning, or especially to do it forward. But now let's see how you can really connect all of what we have learned from this lecture. I will not do this really in detail right now, right here, and maybe a little bit more in detail for the review lecture, the video. I will try to get more information. But here I would like to really give you a overlook. So the lecture flow, you're familiar with this diagram, and probably you're already fed up with this diagram. So this is exactly what I intended to, because this is the really global piece of message for you to remember to take away from this lecture. So to, first of all, understand there are 4 elements when we talk about materials. So materials are actually everywhere. Even if you talk about the digital world is constructed via physical materials. If we don't have chips or so, nothing will work. And second message is there's actually a methodology of learning. And I hope you got it. So we're trying to give you this methodology at every lecture, at every, let's say, concept or dot we were studying. So basically this is related to this 3 kind of concept I'm illustrating here. So characterization, theory, and modeling. So we always go via, let's say, observation of phenomena and characterize it, and then we formulate a theory. So the theory could be qualitative or quantitative. So if it's quantitative, it is a equation or a sense of equations. And they're super, let's say, abstract and directly to the point. And modeling is finally responsible for explaining everything. So with the modeling, especially FEM modeling or other kind of modeling technologies, you could kind of make a digital twin of what you see in the world, with complicated shapes, with complicated kind of boundary conditions, to really see the theory is working there. So these are 3 very important ways to learn stuff. So you probably benefit from this lecture. You could even benefit this kind of way to learn from other lectures. All right, let me just go a little bit fast forward here to get all the components out. So probably you are familiar with it already. But if you forget a little bit, don't worry. I will really walk you through in the review lecture tomorrow or Thursday. And as I said last week, we basically built this kind of loop for you via metals for the past, let's say, 4 to 5 weeks. Last week, we kind of really solidifying things, especially concerning the structure and the property, and with another material, with a ceramic material. So that is one add-on we gave you. And today actually is about another add-on. Another add-on is on the property part. So we said we would like to kind of strengthen a little bit on the structure-property relationship, because this is more related to material science. And for the material engineering part, we believe with what you have learned from lecture, it will be easy to find, let's say, applications and to understand text and to study on your own. So today we're focusing on add-on about property, and it's about the physical properties. So we were speaking about mechanical properties, maybe you realize that, since it is the, let's say, main application of materials. So to support structures, to build stuff. And actually there's not just the mechanical property, right? In the world, we still have a lot of other properties, thermal and electrical, optical, and magnetical, and all these properties. So we will not cover all of them. We will today mainly focus on thermal and also a little bit about electric. And we will basically omit the optical and the magnetic properties. You could read on your own for those two parts, and we will not really talk about it. We will not also put it into assignment or exam. So you should be rather focused with the thermal and the electric that we're gonna go through today together. All right, so that's the basic instruction of today's lecture, and we will begin with the thermal properties. And this is the, let's say, learning objectives. We basically have, let's say here, 6 points. So they're illustrating the keywords that you're gonna learn and you will be able to describe or able to understand. But they're actually categorized into 3 main categories. So the first part we're gonna learn is about the heat capacity. So maybe you know this word, I guess. And we will basically define it in a proper way. And also to be more specific, we will define the specific heat capacity. And after the definition, so you could know that's about the characterization basically. And then we're going to go to, let's say, the theory. The theory is related to the mechanism. So what is the primary mechanism for, let's say, heat capacity, because that is related to how the thermal energy is stored in our material. Yeah, that is a new perspective you probably didn't know yet. So especially it is telling the essential about temperature. So what is really temperature? Yeah, this is could go really deep. It is very connected to let's say quantum mechanics. If you want to go that deep, we will scratch a little bit, not that deep, but you will really see some, let's say, essential mechanisms about thermal energy and temperature to understand it better. And the second part we're going to cover is about thermal expansion. So you know this pretty well, because this is very much correlated with, let's say, daily phenomena and also engineering applications. We will define the linear coefficient of thermal expansion, and you will be also learn what is the sense of it. We'll give you one example about it. And of course, we're going to go to the mechanism of that as well. So you probably remember at our day 1 lecture, we already touched a little bit, but not that deep. So today you will really get a better sense about the mechanism of thermal expansion. And this is related to the potential energy versus the interatomic separation plot. And the last part is about thermal conductivity. You see, these three things are really confusing, yeah, but they're also well connected. If you think about one application in your daily life, actually, these three coexist. Yeah. For example, when you just do a cooking, yeah, when you do just a cooking of your anything, and you put your pot on the oven, and you are trying to cook something. Actually, let's say the metal, the pot made of steel probably is experiencing three of them. So heat capacity, because you're trying to give, let's say, energy to the pot, so that the pot could get a higher temperature, right? And then the temperature should be conducted, the energy should be conducted into the water. In your pot, you're probably trying to do some spaghetti or so. And something you don't notice for that application is there's thermal expansion. Yeah, not that much. You probably don't sense it because the object is rather, let's say, uniform and not that big. But actually, the thermal expansion is also happening because your pot will go from room temperature up to something like 100 degrees C, right? Maybe not that high, yeah, at least not that high from the outer layer, but inside it's close to a hot temperature. So as you can see, all of these three are working together, and they're also kind of confusing. So we basically will walk you through about what the three concepts are, and you will be able to describe them individually. So for the thermal conductivity, we will also explain you the principal mechanisms for this, for metals especially. All right, that's the opening of our today's lecture on thermal properties. So here again, I'm trying to illustrate these three guys all together. So they belong to the thermal property family. So there's no need to define what is thermal property. Yeah, basically anything related to temperature is something called thermal property. All right, let's begin with the heat capacity. So what is heat capacity? So here you could know the heat capacity is ability of a material to absorb heat. And that is simple. So first of all, we need to know, yeah, what is heat. So heat is kind of energy. Maybe you get a sense of it. Yeah, to describe the, let's see, the heat capacity, we already have a equation over here, and the equation is defined like that. The energy required to produce a unit rise in temperature for 1 mole of material. So this is the heat capacity of material, or to be more specific, this is the specific heat capacity of a material. Yeah. So its specific heat capacity of, let's say, steel is the energy that required to produce 1 unit rise in terms of temperature. So 1 unit rise could be the unit of degree C or Kelvin. Actually, they're the same. They're just shifting. And for 1 mole of material. So it's a unit material. It's not, yeah, extensive. So heat capacity is an extensive measure, but specific heat capacity is an extensive measure. So it is applied to unit material. And how do we describe it? So actually the heat capacity or specific heat capacity is something defined very similar to this kind of energy over, so the energy input to 1 mole over the temperature change, so dq over dt. So this is a very simple definition. Let me just get the pen. But most often we don't use mole. Yeah, maybe what you're familiar with is this kilogram. So it is a unit material that could get a unit temperature rise for with this required energy. Yeah, that is the definition about specific heat capacity. So this is the unit of it. Maybe you can get the sense why it is defined that way. And here is about two, let's say, ways to measure the heat capacity. And the first way is measured is at the constant pressure. And the second way to measure heat capacity is at a constant volume. So these are two different ways. The constant volume is called CV and the constant pressure is called CP. Maybe you're more familiar with this CP because this is the heat capacity we're using for daily life. And usually the CP is bigger than CV. And you might wonder why is that? So this is actually pretty easy understanding if you have learned thermomechanics or so. But before you learn, maybe I could give you a simple, let's say, illustration about this. Let's begin with the CV. So we know for temperature, so we're not giving you the kind of essentials about temperature, but you should probably have the sense. So temperature is basically representing the energy. Temperature is a way to illustrate the energy, or to be more specific, is the internal energy of a system that has. So if we have the kind of CV basically used is, let's say we define heat as Q, and if we just kind of put this heat completely to a system, and the system does not change its volume, and this heat is completely converted into the so-called internal energy, so U, and this is the kind of basic sense of to define a CV. Then you can use delta Q over delta T to define your CV. This Q as equal to U, and the U is related to, let's say, the delta T. But if we define our heat capacity via a constant pressure, so this gives a little bit different, because in that case, if you just gave a dq, let's say you gave small amount of energy to the system, and that will of course introduce some increase of temperature, and that is reflected to this du, right? But as you have a constant pressure, this is something you have to think about, because it is already related to the second concept we're having. When you have the increase of temperature, our materials will most often get this what? Thermal expansion, right? So that means when you have the increase of temperature, that is really getting messy. Let me just try to clean a little bit. All right. So because you have this kind of change of volume, right? A change of volume or change of length in a way due to thermal expansion, actually you will cause a little bit, different work. And this is something maybe you're familiar with. This is something we call it work. So in this case, the heat that you gave to the system is not only used for the increase of temperature, it is also caused the kind of additional work to do. So in that case, if you just use the dq to calculate the heat capacity or specific heat capacity, you will have a rather larger one. So that's why the CP is usually bigger than CV. So I hope now you got it, why these two are a little bit different. And for our daily use, actually CP is more preferred, because it's usually the case we could control the pressure and not the volume to be very precisely. All right. So that is about the heat capacity, and here is the unit once again. And if you are more familiar with the British system, and this is what you get. All right, the heat or specific heat capacity is not a constant. It is rather dependent on temperature. So maybe you could also easily understand this, especially when I just gave you about the mechanism about heat capacity and the essentials about temperature, you would understand better. But basically, you could say when we have absolute zero here, your heat capacity is zero. So when everything is at absolute zero temperature, no matter how much kind of heat you gave to a system, the system will not be able to increase their temperature. And this is a very interesting concept. And basically, when you just increase your temperature, and the specific heat capacity will increase. And when there's a threshold is met, this is the so-called Debye temperature. This is a temperature which is usually less than room temperature, so close and less, so not higher than room temperature. And the specific heat capacity will tend to go to a constant. So especially the CV will tend to go to a constant, not the CP. And this constant is equal to the 3R. So the R is the gas constant. And this is a constant not for, let's say, only one material. It is an upper limit, or it is a kind of constant for almost all engineering materials. So this is a limit that no material could exceed, but not meaning this is a limit every material will reach when we just get a high temperature. But in a sense, our materials are not too far away from each other when the temperature is high enough. So that is related to the essentials about heat capacity. Now we're going to just tell you what is the essential, or what is the mechanism about heat capacity. And to understand that way is because heat capacity is related to converting energy into the unit rise of temperature. Basically, we need to understand what is temperature, right? And what is the way to store the energy in our system. So the mechanism to store the energy, or the mechanism of temperature, is basically via atom of vibration. So that, in another word, is expressed as energy is kind of stored as atomic vibrations in our systems. So this is a rather, let's say, difficult concept for you to understand. You probably could relate to, let's say, the molecular vibration, right? The Brownian effects, our moleculars are kind of moving and so on, but that's not exactly the same. So here we're talking about atom. So for the Brownian effects or so, we're usually referring to liquid or gas, and that is kind of related to the kind of molecular atoms, motions. But here we're talking about atoms. So meaning when you talk about solids, there's also atomic vibrations. And I will just show you next slide what they look like. And basically that means when the temperature increases, so when you just gave energy to your system, that energy is reflect to the increase of temperature. So that means the energy is stored in the system via atom vibration. So when temperature is higher, is increased, the kind of average energy of the atomic vibration increases. So this is the basic concept. Now let's just look at some phenomena and how the kind of atomic vibration is looking like. And so here I'm giving you let's look at, first of all, the top figure right here. So I'm giving you a lattice. So this is just a simple lattice, let's say, and with or without some dislocations or vacancies. Let's say here's one vacancy probably. So this is a lattice, and the orange means everything is regular. So if you just look at the orange kind of lattice points there in a regular pattern, and you might think, okay, my atoms are just sitting like there. For example, steel or aluminum, steel in BCC, aluminum FCC. They're just sitting there still. They're not moving at all. They're just being good over there. It's not truth. We didn't specify this. We didn't really emphasize this when we talk about FCC, BCC, when we talk about atomic structures and so on. The fact is actually the atoms, they're not sitting still in the solids. They're vibrating. They're vibrating even in a quite extensive way, because that means they're vibrating with a very high frequency. But why is that? So why is that is related to thermodynamics. We will not explain why is that. But I could tell you one, let's say, evidence of that. Maybe you remember when we talk about diffusion, one of the way to make diffusion is the interstitial diffusion. Yeah, but the other is so-called, maybe you remember, is substitutional diffusion or self-diffusion. So the atom could really switch places. So this atom will go there and the other atom will come here. And you didn't ask why the atoms would do that. Yeah. So here is the explanation. Because the atoms are really vibrating and the amplitude is not that small. Via this kind of vibration, it is very easy to switch a position. So why this atoms is vibrating here, for example, if you look at the blue, so the blue is kind of indicating how much the atoms could be really switched, shifted from its original place to another place. Yeah, so it could go that wild. Yeah, for example, this one could go this direction. So when atoms are doing this kind of vibration, it is possible for them just to get another place from one lattice position to another lattice position. Yeah, so maybe that helps you to understand better about diffusion as well, why diffusion is happening. And once again, this kind of vibration is, maybe you could imagine, is related to temperature. So when we have absolute zero temperature, at that temperature, your atoms are still. So they're not moving anymore. And that's why at that temperature, your CP is going to be zero, because you cannot trigger the atom vibration anymore. And that's why the energy will not go to the system. And the bottom figure here is showing you how the atoms are kind of vibrating. So they're not just vibrating like Brownian effects, so randomly. Actually, they vibrate in a very specific pattern, because here we're talking about energy. Yeah, it's not a random thing. So here you probably should just neglect the black curve. Black curve is telling you something that is more complicated. We're more referring to the red curve. So if you just focus on these three, let's say, black dots, yeah, they could refer to your atoms. Yeah, so the atoms are just moving, like or vibrating, like a wave, as you can see here. Focus on the red one once again. If we just talk about wave, maybe you remember we need to think about two things. One is the amplitude, the other is the other is the frequency, right? So you can see here's the amplitude, for example, this atom is moving like that, that high and this low. So this is not very significant. The significant thing is about the pattern, because the atoms, they're not moving like individually. They're actually moving in a system. So the system will basically to formulate a transmission of wave. So if you look at the red curves, basically we're kind of transmitting a wave via the vibration of these three atoms. So they're not just moving randomly, they're actually in a system transmitting this wave. And the second thing is about the frequency. that is related to a very important concept. This kind of energy, or the atom vibration energy, have two forms. One is lattice wave, the other is so-called phonons. Yeah, phonons is something in the quantum mechanics. It is referring to this kind of energy transmission, because this transmission is not slow. Actually, it is in the speed of sound. It's very fast. And it is like somehow we're transmitting the sound in the solids. So this is like the way we're transmitting, let's say, energy in our solids. It's like transmitting sound in kind of solids when you just hear things. But to describe this kind of particle-like thing, this phonons, maybe it's easy to make analogy when you just talk about probably photons. Yeah. So this is something about light. Yeah. And one Mr. Albert Einstein kind of discovered this. So light is also energy. Maybe you could imagine. And it is also having two forms. One is the wave form, the other is particle-like form, right? And the most important recognition about photons, about light, is that the energy is not continuous. So it's exactly as we're talking about here. The heat, the kind of energy we're transmitting via temperature, is also not continuous. Yeah, it's in quantum. So for the photons, maybe you remember the energy E is equal to what? It's H times nu. So H is the Planck constant, and mu is what? Is the frequency, right? So that is telling us the energy, first of all, is not a continuous way. And the second point is it is kind of related to the frequency. And if you just make an analogy about the photons with our phonons here, and now you could really get a sense about atomic vibration and how, let's say, the heat or how temperature is really about when we talk about atomic vibration. Yeah. All right. So I think that's enough about quantum mechanics. So if you're interested in it, I think there's one subject about this in your major or in your minor to study about it. And we will not elaborate further in this course. And finally, I would like to give you a list of comparison between the specific heat. So this is something you probably really less familiar about. So we have actually polymers as the winner here. So it has a specific heat with 1,000 or 2,000 or so. And followed that is ceramics. And finally, we have metals. Maybe you feel like why this is looking like a trend. So here, once again, we're talking about, say, P, yeah. We just 2 slides before we're talking about actually that was about CV, but anyway, they're not significantly different from each other. We tend to formulate a kind of constant for the CV when the temperature is high enough. Why we have here somewhat so different values, even to a kind of matter of 1 magnitude. What you should pay attention is really about the unit. So the unit we're talking about for the CV or so is really in mole. But here, as you can see, the unit, as I already told you at the very beginning, in engineering world, we tend to use the density. We tend to use kilogram. And maybe you could now understand why they're different and why polymer is having the largest specific heat capacity. Okay. And okay, that was my question. So that was enough about heat capacity. I hope everybody got it. And now we move to the second concept, which is called the thermal expansion. And this is something you're probably very familiar with. and we don't really need to explain the phenomena too much in detail, because if you just still rely on the conventional thermometer, you know it very well. So that is especially designed via the concept of thermal expansion, and even the concept of the linear thermal expansion. But here I would like to give you the equation to describe it, the equation to characterize it. And how to characterize that is, let's just imagine we have a kind of a linear object. So this is the guy here. So we don't care about the volume or the width. So we only care about the length. So let's say this is the initial temperature, and we have the so-called initial length of it. When we just kind of increase temperature to a higher one, and this is the final temperature, the length is kind of increased. And how to describe this, or what is the equation governing this phenomena? It is like this. So when we use the final length minus the initial length and divide by the initial length, so this is important, divide by the initial length, and then we can find a correlation with the temperature. So here is one constant, it's alpha L, and this is so-called the linear coefficient of thermal expansion, and times the final temperature minus the initial temperature. So as you can see, here is delta T, yeah, and on the left-hand side we have delta L, and over what? Over L0. So if you just try to rearrange this equation, maybe I can write it here, and you would find the definition about alpha L. So we would have delta L over L0 is equal to alpha L times delta T, right? So this would just give us something like alpha L. So the linear thermal expansion is equal to 1 over L0, right? This is this part times delta L divided by delta T. So this part is basically the length change, and this is the initial L. So if we just think about what you're having in a daily life, you could definitely make this correlation. So the delta L is with the delta T is in a linear relationship. Yeah. All right. So that is about the thermal expansion. So I think everybody got it. We don't explain why it's in a linear relationship, because that will kind of relate to some deep derivation from quantum mechanics point of view. But you basically kind of know the concept about that. Here, I would like to really give you an explanation about the, let's say, the mechanism for this thermal expansion. Yeah, and this is a diagram we have seen already in the day one lecture. Yeah, because we said the thermal expansion in a way is related to this plot, the potential energy versus the interatomic distance or interatomic separation about our atoms. And but why we didn't explain in detail. Let me just remove this line. I think this is something extra, but it's not happening here. Okay, anyway, so this is a curve you typically see, the thick red one. So we said, okay, when we just vary the atomic distance, we will have usually such a potential. And here is the kind of energy minimum the atoms would prefer to stay comfortably there, right? What we didn't specify over there in the day one lecture is that this minimal energy is only related to absolute zero. So usually you cannot reach that energy. And you can only reach that energy when you have absolute zero temperature. Why is that? Maybe you just remember what we talked about, the atomic vibration, because atomic vibration is always there. Yeah, when you have temperature higher than absolute zero, you will always have atomic vibration, because when you have temperature, basically, meaning your system has energy. So it's not completely still. There's energy in the system. So when you have higher temperature, when you have the atomic vibration, now you can understand why we cannot reach this energy, because your atom will not stay still, like R0 here, not moving at all. So assuming you have a T1 temperature, which is corresponding to actually a E1 energy here, the kind of atomic will start vibrating via such a, let's say, amplitude or so. You see the distance of this energy E1 is not a value, but rather a band. So if we just increase temperature up to E5, or correspondingly to temperature as T5, you see the atom could just comfortably stay with the Saturn range. So this is related to the atomic vibration, actually. So that means when you have higher temperature, the atomic vibration is getting more excited. And if you just try to correlate the mean value, so this is thin red curve is trying to give you a sense about the mean value, but actually it's not that precise. Let me try again here. So this is, let's say, the mean value of your, okay, that's perfect. The mean value of the kind of atomic separation, or the interatomic distance. You see, this kind of mean value is getting higher and higher. So it is from this R0 up to R5. Yeah, maybe finally now you know why we're having thermal expansion, and because the mean value basically is telling you macroscopically how large is the material. So if your interatomic distance is getting larger, and eventually it will lead to a, let's say, a larger material if you observe in reality. And this is the reason for the thermal expansion. Maybe you kind of sense it. We could have this kind of phenomenon is only because this kind of potential curve is not symmetric, because it gets basically wider when you just go to the right hand side of R0 and then the left hand side of R0. Yeah, so meaning this curve is asymmetric. So on the other hand, if we have a symmetric kind of potential energy distribution, so this is the symmetric one. So basically this is our R0, but when you just get higher temperature, so your atoms are becoming more excited with vibration with a higher temperature. Because it's symmetric, so it doesn't really change the mean value. So the atoms are vibrating a little bit more dramatically, but this will not lead a thermal expansion. Yeah. So because the average kind of average distance is not increased. So the thermal expansion is happening only due to this kind of asymmetric curve of the potential energy over the interatomic distance. All right, I hope now everybody got it. There are two important things about this explanation. So the first thing is related to the kind of atom vibration. So when you have higher temperature, there's higher kind of atom vibration. And the second most important thing is this potential energy curve is usually unsymmetric, and that is leading to a kind of increase of the interatomic distance, finally a higher length or higher volume about the thermal expansion. All right, I hope everybody got that. And if I could just give you maybe one more concept is related to the thermal expansion is here we're talking about linear thermal expansion. So this is R for L. So L is denoted here as linear thermal expansion. But in reality, we're not talking about linear object, except for the thermometer here. But when we talk about engineering structures, actually we're more talking about let's say the thermal and the kind of volume change, and not just the length change, but the volume change. So maybe in reality, what you see is alpha V. Yeah, so this is the volume coefficient of thermal expansion. And usually this value is 3 times larger than this alpha L. Yeah. All right. So that's enough about the mechanism of thermal expansion, and also like the heat capacity. Here I'm trying to give you a comparison between different engineering materials. And here once again we have the polymer is leading here as the highest thermal expansion, and then followed by metal, and finally it's about ceramics. I think here is something you know pretty well, because the thermal expansion is deep down really related to the kind of atomic bonding. There is indeed atomic vibration and also the asymmetry of the current, but finally what decides is atomic bonding. Because polymer, maybe you remember, we have the bonding as the weakest. It's the weak secondary bonds. That's why we usually have a larger thermal expansion coefficient. If you just compare the potential versus the atomic, this is bad drawing, but you know what I mean. When we just talk about higher energy and low energy. So the ceramic basically is having the hardest bonding, which is the covalent or what is the other one is ionic bonding. That's why these ceramics are having really higher, lower thermal expansion coefficient. All right. Okay, I think now it is time for us to take a break. And when you're back, I'm going to give you one example about thermal expansion. And we said about the thermal expansion, and now I'd like to give you an example about thermal expansion. The example is actually pretty simple, and you can imagine it as, you know, many engineering applications in your daily life. For example, when we talk about a copper wire, which can be used for electricity, for example, right? And it can also be something else. When we just talk about one example about the skiing, in any kind of equipment, we need these wires to transport the people from downhill, uphill. And over there, we're also talking about a kind of wire, maybe not copper over there, rather steel, but it's a wire. So the example is like a copper wire with a 15-meter long is cooled from, let's say, 40 degrees C to -9 degrees C. How much change in length will it experience? And this is a quite important design problem, so engineering design problem. So when you really add up with a job for product development or so, and this is a concept you have to have during the design phase, because especially for countries like Finland here, and in hot summer, we could experience something, maybe not 40, but at least 35 or so degrees C. And when we go to winter right now, I just checked the temperature, it's around about -14 degrees C. This is still not the coldest, right? Maybe for you, this is the first year in Finland, and on the first winter in Finland, you don't experience the coldest. So we could add up -20 or so in January or February, or even more extreme when we go a little bit north. So the temperature change is around about 50 to 60 degrees C. Yeah. And this is a range you should kind of aim at. When you just design something, you should expect for the Nordic countries there would be the temperature range about 50 to 60 degrees C. And what kind of thermal expansion we're talking about here? And I'm not asking you to do, but I would rather show you how it looks like for you to get a feeling about it. So for copper, actually, we're having a thermal expansion, something with a magnitude of 10 to the power minus 6. And not extremely small, but also not that high yet, rather medium. And let's say if we just use the equation, so maybe you can see it's the simple one, because we're talking about linear case. So the delta L is given by such equation. And if you just take everything into it, you will see the delta L is around about 12 millimeter. So 12 millimeter is something pretty small compared to 15 meter, of course. But this is not something you could neglect. You will really see it. It's close to the diameter of 1 cent. You could imagine that's not nothing. If you just make a, let's say, a neglection of it, and it could result something significant. Why? Because the very important concept related to thermal expansion is so-called thermal stresses. So of course, thermal expansion could lead to some other issues, especially when we talk about geometry, precision. But for the engineering applications, the most important impact of thermal expansion is the stresses, the thermal stresses that is introduced by it. Maybe you kind of already could imagine when we just have, let's say, the wires going through a certain distance, and it is okay if the wire is just lying there without any, let's say, force or without any restrictions to it. But just imagine if you want the wire really keep straight and you are already kind of describe a tension to it. And if you imagine when it goes from summer, say you just design it in summer, and when the wire kind of goes to winter from summer, you would imagine the kind of contraction due to this thermal expansion or thermal contraction is going to develop the kind of tension strength, right? You could imagine about that, because it would like to contract, but due to the kind of describe the tension strength or geometry, it couldn't. So that will basically develop a thermal stress or thermal tension strength. And we could actually use, let's say, the simple Hooke's law here. As you can see, we're just giving the stress is equal to the E. So assuming everything is isotropic, and this is what you get, right? This is the delta L divided by L0, this part, right? And you can imagine this is giving you a kind of estimation about the thermal stress we probably could have. And finally, you could calculate in such a way. So this is the stress you could use to make an estimation, but you should think about this stress could be really decremental if the extent is very close to, let's say, if this stress is very close to plastic deformation, even more severely if it is close to the failure stress that your material could have. For example, when we talk about steel, you remember when the temperature is low, we could have the kind of ductile brittle transition. And when we have ductile brittle transition, you really could have the fracture in the elastic regime that could be led by thermal stresses. So this is just talking. And now I would like to give you one example about really this thermal stress-led failure. And this is so-called thermal shock resistance. this is not just specific for, let's say, for wire. It is actually general to any materials because this is related to one heat treatment process. It's so-called, let's say, heating and cooling. So especially when we just do the quenching process with a fast heating or cooling. Because that kind of fast heating or cooling usually kind of induce a non-uniform temperature profile to our material. Maybe remember when we do the quenching, the surface always having a higher temperature decrease than the center. So you probably have a higher temperature and center than a rather low temperature and surface. So if we just try to make it abstract here, so the thermal gradient on temperature gradient just into two layers. Let's say we have kind of two materials, for example, the surface material is a coating and the kind of substrate is another material. And due to the let's say, quenching process or due to the material property, let's say, because this one probably has a higher thermal expansion than the middle one, right? And you could really have a really kind of cool temperature at T2, but rather high temperature at T1. Yeah. And because the temperature T2 is much smaller, that will develop a, right? That will develop a higher kind of thermal expansion or thermal contraction than the middle material. And due to this, two materials are connected to each other, right? They have to go as a whole. So this material cannot shrink as much as it wants. So the bonding is always here is restricted. That will develop a kind of tension, yeah, for the surface material. I think everybody could imagine that, right? Because the material wants to contract, but it cannot, and then it kind of stretched. So that's why we're going to have a tension stress here. It is a sigma. And by the equation you just learned from the slide before, we could use a simple Hooke's law to describe this kind of stress. So this is so-called the thermal stress. Yeah, it is exactly related to the difference of the temperature, right? The T1 minus T2. Yeah, because we're talking about now relative ones. And how is this temperature related to the kind of process? Maybe you could imagine if we make a very fast quenching, so the temperature change is so fast, the T1 minus T2 will be larger, right? And if it is so slow, if you just think about the dream case, the quenching rate is so, let's say, so small, it's almost, you know, kind of isothermal cooling, you would have no kind of difference. So you will not develop any thermal stresses or kind of thermal gradient over there. So that will give nothing for that. So that means we would have a kind of proportional relationship between the temperature change and the quenching rate. And as I just described you, we would expect some fracture of our the layer material, the surface material. So let's assume it's a rather simple kind of case, but you could imagine when we have cleavage fracture, this completely makes sense, right? So we set a critical stress sigma F, which is kind of representing the failure stress, meaning when the material is reaching the sigma F, we will get kind of fracture. So if we just take the sigma F into this equation right here, you would derive a kind of limit delta T. So when the T1 minus T2 is reaching this value, the sigma F divided by, because these two are constants, right? Material constants. Divided by this value, so we will trigger fracture for the material. And T1 minus T2 is related to quenching rate. So finally, the failure of the layered material of the surface material is related to quenching rate, right? That's why we kind of have this so-called limit quenching rate or thermal shock resistance, meaning we cannot apply a extreme quenching rate to our materials, because if this kind of quenching rate is too high, it will finally trigger already a fracture. This fracture is caused not by mechanical loading, but by thermal loading, by kind of thermal stresses. All right, I hope everybody got it. And this is something very much related to product design. When you, in the future, join a company developing products and or processes, you should always think about, thermal expansion, and always think about the thermal gradient you might trigger, and that could lead to really decremental events. For example, fracture or thermal shock resistance. All right, I think that is the basic topic about thermal expansion. So as you can see, we kind of invest the most time to that, because that is really an important topic for you. So I hope you could really get a sense of it, understand equation to do the calculation, and also understand mechanism. And finally, you could apply the equations to guide your engineering design. All right, the last topic about thermal properties is thermal conductivity. And this is something we will not elaborate so much, because you might learn it in detail. And I mean, I'm talking about the guys who are in the computational engineering subject. You will learn this definitely in detail when you go to the thermodynamics and heat transfer course, because that is exactly designed for that. We will basically give you some, let's say, basic knowledge here, and you could really get a sense of it. And most importantly, you probably could connect it to something you have learned. So first of all, what is thermal conductivity? The definition is that it is ability of a material to transport heat. So that is pretty simple. That is giving you a, let's say, qualitative description about thermal conductivity. And for a quantitative description, that is related to the equation right here. So this equation probably reminds you something. It is called First law. But if you just try to think about this equation, I mean, this equation could be similar to many things. But first of all, I will give you a definition about this heat flux. Maybe this is your second time to see, at least in our lecture, about flux. Maybe remember what is the flux by itself. It is describing a kind of speed, but not a normal speed. It is a speed via a unit area, right? That's why if you just look at the unit, we have a meter square. And before, when we talk about diffusion, actually we're talking about mass. Maybe you remember that. So when we talk about diffusion, we have the M divided by A times T. And we call this is a kind of mass flux, right? And for heat flux, we're talking not about mass anymore. We're talking about the heat transport. So over there, it's mass transport. And that's why for the heat flux, basically it's Q. Q divided by A times T. So this is so-called heat flux. And to describe this quantity, we use in the small q. The big Q is accumulated heat, and the heat flux is using the small q. And that is equal to what? Is minus K, so K is constant. It's so-called thermal conductivity. So thermal conductivity basically, as all the other kind of quantities, thermal expansion and also thermal heat capacity, it is a concept, as at the same time, it is also a quantity. So you should always remember what it means in one sentence. So the thermal conductivity is ability of material to transport heat. But at the same time, the thermal conductivity is also a quality. So it is described by this K. So this is a value to basically describe the thermal conductivity, and the times dt over dx. Maybe now you can really get it. So dt over dx basically it's a temperature gradient. This is exactly similar to the fixed first law. Remember? So the diffusion, the driving force for diffusion is the concentration gradient, right? It is dc over dx, maybe remember? And here for the thermal transport or the heat transport, the driving force is temperature gradient. So basically the heat or the heat flux, to be more specific, will basically go through from a higher temperature place to a lower temperature place. Yeah. And the basic kind of description is given by this equation. It is the Fourier's law. Yeah. All right. I think now you get it. We could also give you a kind of mechanism description about this. Yeah. And it is once again related to the atomic perspective. You can already imagine. So as we said, what is the essentials about temperature? So temperature is described by the atomic vibration, right? And here for the transport of heat. So keep in mind, it is different. So heat capacity is different from thermal conductivity. Yeah, heat capacity is the energy that you require to increase your temperature, right? And the kind of conductivity is basically to transport the heat. So it doesn't mean the material has to go that high in terms of temperature. It is more like the transportation of the heat. It is correlated with atomic vibration, yeah, because that is related to temperature. But more importantly, it is related to the free electrons. Yeah, so there are two mechanisms for the thermal conductivity, for the heat transportation. We could do that via atomic vibration, and we could also do that via free electrons. Yeah, now maybe you remember. You could imagine how the free electrons could do that, but we will not basically elaborate that in detail. We will rather give you a kind of comparison directly. So once again, we're giving you a ranking of these three engineering materials we have. As you can see here, we got metals as the winner, yeah, and followed by ceramics and polymers. Why metals is the winner right here? It's simply because metals could have the atomic vibrations as the transformation mechanism. It could also have the free electrons because they're, the metals are connected via the metallic bonds, and the electrons are basically falling in the electron C. That means they are all free. So all of this kind of free electrons could do the motion easily and could transport the heat easily. And followed by that is ceramics. So ceramics, they could do atomic vibration easily. And for polymers, it is difficult to do the atomic vibration because they have the very thick connection about their long moleculars, and they could be kind of conduct the heat via vibration of atomic and also this kind of molecular change, the rotation and the vibration about this molecular. That is the ordering about these three engineering materials. Now you could see why they are having such a different performance in terms of thermal conductivity. And that's all. All right, I think it is time for us already to get a summary about the thermal properties. And we basically talk about the three properties of the thermal behavior. And first is the heat capacity. Yeah, you should be able to describe what is heat capacity. It is the energy required to increase more of material by a unit temperature. And the mechanism of it is correlated to atomic vibration and what is the essential of temperature. You can understand that. And the second, we talk about thermal expansion. Yeah. And why we have different values for different materials, and what is the mechanism about thermal expansion, not to atomic level, but rather let's say interatomic distance level. And the third point we discussed is the thermal conductivity. That was just talked about. We have a little bit of emphasis in the thermal expansion because over there we gave you most knowledge about calculation, as this is a very engineering related topic. So you're asking a little bit more than the other two to master in our course. All right, but in general, that was all about thermal properties. And now we move to electrical properties. Actually, this would be really a scratch on the surface. So this is rather a little bit far for all of you in terms of your future development. And that's why we're not giving you details. So this is basically a simple recap as what you learned from high school. And then we try to elaborate that in a little bit sense with this kind of flux theory. So here's a list about the learning objectives. So the first of all is the famous Ohm's law. So I think you know it already at the moment. But we will try to give you a redefinition about Ohm's law. Maybe that's something you could have a better connection about what we just learned in the thermal property. And after that, we will define the electrical resistivity and conductivity. So these are two important concepts when we talk about electrical properties. Now you would know, I think everybody knows what they mean, let's say qualitatively. And hopefully after this lecture, you would know what is the quantity that is representing these two properties. And then we will basically kind of ask you to calculate the sample resistance, given the knowledge about resistivity or conductivity. How could you calculate the resistance of your sample? And finally, we will try to make an ordering, again, make a ranking about our materials in terms of their electric conductivity. All right, so this is the Ohm's law, because we're mostly caring about electric conduction. And you know this law is described by Mr. Ohm first. And it is written like V is equal to I times R. So V is the voltage, I is the current, and R is resistance, right? So V and I, these are something we could measure, and I will not elaborate in this lecture. What is connect to our materials perspective is R. So remember, this is called resistance, and resistance is not material constant. So it is, once again, extensive measure, because the resistance is finally defined by one material constant. It's so-called resistivity. So the resistivity is kind of denoted by rho. Its definition is a material property that is independent of sample size and geometry, right? And basically, this is a material constant, and the resistance of your material is defined by rho, the resistivity, and the length of your sample, and the cross-section area of the current flow. So I think everybody knows this equation. If you don't, now you got it, but you could easily have an imagination about it, right? If your material is basically having a long length and a smaller area, so we're gonna have a larger resistance, right? But the resistivity is a material constant. It is related to the material. So how to elaborate or kind of think about the resistivity, it's easier to think about the reverse of it, the so-called conductivity. It is denoted via sigma. So now, as you can see, this is really a different world between the electrical world and the mechanical world. And because sigma is a value we are using so often in the mechanical world to represent stress, which is so often C. And in the electric world, they're using it to represent something completely different. Once you want to do something together, you will find difficulty. But as you can see, we're not running so many problems that electrical and mechanical properties are coupled. That's why the problem is less. Usually it's mechanical thermal properties are coupled, and we have most common language over there. All right, so the sigma, the conductivity is basically 1 over rho, so 1 over resistivity. Now you can easily connect these two qualities. And if we just gave you one example to realize what is about this resistance in connection about resistivity, you could easily think about this two, let's say, kind of samples or wire of copper in a way. We could just use that equation to calculate the shorter and thicker sample will give us a much smaller resistance than this long and thin one. Yeah, this is about the resistance. So you just need to remember resistance is always geometry dependent. And now we're going to give you a redefinition about Ohm's law. Yeah, because we don't like when we just use that kind of R, the resistance, which is an extensive measure, which is sample geometry dependent. We want to give you a, let's say, material dependent measure. So that's why we're going to redefine this Ohm's law into a flux term. So here you can see the J is representing not the density anymore, but actually it's a current flux. Sorry, not density, not the current anymore. So it is defined as the current I divided by a surface area. So divided by A. Yeah? So exactly like a thermal flux or mass flux, which is diffusion. So here we have current density or electric flux. And here we have one quantity, which is a let's say a material measure. It's the sigma, it's the conductivity. Yeah. And this kind of complicated Greek number, I forgot how it's called, epsilon, right? It's the capital epsilon, is so-called electric field potential. And this is the V over L. Yeah. Or you can write it also as dV over dL. All right, if you just go a little bit forward, if we put it into a coordinate, then you could write it as dV over what? Over dx. All right, and then if you just put everything together, I think now you can finally get a really sense of it. This is exactly looking like the fixed first law or the first law for the thermal conductivity. And now we have this so-called redefinition about Ohm's law in the flux term. And here is the electron flux, and here sigma is the conductivity. And this is exactly what we're talking about here. So this is so-called voltage gradient. So basically the driving force for thermal, for electrical conductivity is the gradient of voltage. Yeah. Exactly the same as the gradient of temperature and the gradient of concentration. So they're all the same. All right. And now, as usual, we'll give you a comparison of this electrical conductivity of all the materials we have. So as you can see, metals are the winner here, yeah, because we didn't emphasize the mechanism about electrical conductivity. It could be very kind of comprehensive to talk about it, but it could be also very simple. You just imagine the electrical conductivity is related to the free electrons, right? Then you can basically freely move from one place to another. And that's why metals are basically the winner, because they have a lot of free electrons to move. And that's why they're so-called conductors. Their electrical conductivity has a magnitude of 10 to the power of 7. So this is huge. And compared to the materials so-called semiconductors, yeah, silicon or so, they have a magnitude of 10 to the power of -4, or even -6. So they're so-called semiconductors. And then we also have the third category, which is so-called insulators. So they're basically ceramics and polymers, because here we're talking about basically 10 to the power of -10 or even -17. You can see they basically don't conduct any electrons. All right. I think that is all for the electrical properties. I mean, we don't really need to summarize here, because we just talked about within the last 5 minutes or so. But anyway, I hope you could now understand better what is electric conductivity and resistivity, especially for conductivity. You could find a good analogy to the thermal conductivity and to diffusion in terms of mass transport. And then you could also understand better these three categories about conductors, semiconductors, and isolators in terms of materials and in terms of the brave mechanism description. All right, now it is time for me to give you a finally overall picture of what we learned during this past 6 weeks. So it's really, let's say, fast. Yeah, you have to acknowledge that you have learned so much during the past 6 weeks. Yes, if you just imagine that tetrahedral I gave you, you touched every corner of it. But what you could really take as a overall picture of this course doesn't mean that tetrahedral picture and overall picture, meaning what you should take really when you go to the daily life, even if you don't become a, let's say, material engineer or product engineer, you become something like a software engineer or so. And what you should think about this world from a material perspective. I gave you the task to build a knife from really nature resources, raw materials in a way. That is actually already giving you really half of the perspective of material kind of. So here we call it cycle. Because we need to think about really at this moment about, you know, the sustainability of the environment and also the sustainability of our material use. You made the practice during the knife making from raw material to, let's say, engineering materials. Basically, we're talking about, let's say, steels, aluminum sheets, and so on. Over here, we're basically doing, you know, all the processes we have used, you have learned, like casting and forging, and also heat treatment and so on. We didn't talk about this process because there's another process which is so-called product design, yeah, and manufacturing and assembly. So because over here, we're gonna finally produce our product. So here we produce our kind of engineering materials, and here we produce the product. So both of these kind of squares will contain a lot of jobs. So many engineers, from mechanical engineer major or material engineering major, or even computational material engineering major would go to these two boxes. But we also have another very large field, which is so-called application. And this could be in various kind of fields, automotive, agriculture, construction, and so on, energy, healthcare, and all this. So this is basically related to application of product. Yeah. And you could imagine many of you will also finally end up with a, with a job over here. Yeah. And we didn't talk about this because this is really related to something more, let's say, practical, not so much about material. But what should be related to in our material sense is how do we deal with the product when they're done with their service. So when your, let's say, kitchenware is done, when your tables are finished, when everything is done with their service, we will actually produce something so-called waste, or even in between their service. And how should we deal with this waste? Because the waste is also made of material. Yeah, there are two ways. So we kind of gave back this waste to our Mother Earth and just put it there as we're doing now with the nuclear waste. Yeah, basically we dig a hole and kind of deposit them there, and as if nothing happened, right? And that's the point. We had no choice for the nuclear waste, right? But for many wastes, we have much better choices, and the choices should be conducted via this recycling and reuse. So if we just do as much as possible for our waste into this circle, then giving back to the Mother Earth, and we really would benefit this kind of material circle and to get this kind of sustainability of materials, because our material is not unlimited. We cannot just dig and dig. There's finally the end of it. And and what is worse is even we gave some waste back to the Mother Earth, because this kind of waste is decremental even to the raw materials. So the much better way is we kind of loop this circle in a really sustainable way, and we could kind of get everything really running smoothly over here. And that is promoting this 3R. Maybe you haven't heard of it, the reduce. Yeah, this is actually perfectly done in this Nordics countries, especially Finland. So basically we kind of reduce our use of materials. We don't need that much of materials actually in our daily life. And then we need to produce reuse. Reuse means we don't go to the, let's say, the processes of making engineering materials. We directly go to the product development. So we reuse the waste or reuse the material we finish into a new kind of product and try to make a circle there. And the final recycle is we basically take our material back to the processing technology and reproduce engineering materials. Yeah, maybe you could find some very good applications of metals. So either steels, aluminums, they're really excellent recycle materials because you can recycle them with a very high ratio compared to plastics or polymers that we have, because they're hard. They're possible to be reused, but they're difficult to be recycled. All right, and also glasses. So we will basically just give you this as a general information. The most important message for you is really, as a customer of this earth and of all these materials, so keep in mind, we try to build up this material cycle, so to make the whole nation, make the whole earth more sustainable and leave good resources for the generations after us. All right, I think that is all for today's lecture. And there's a final message, probably I should I should go back to my slides to show you, which is about this. What is the plan for our exam and also the video lecture tomorrow? This is the main issue for us to settle for this lecture. First of all, you could still do some in-depth reading, especially chapter 19, which is the thermal property. And then the rest 3 are really optional. We will not put that into assignment or exam. You could just try to use it to enrich your knowledge. The review lecture, I didn't write it here, but the review lecture will delivered as a video. So I remember, I think Wenqi and Rongfei gave you a kind of meta survey so that you could ask in that survey any questions or concepts or somewhere you don't feel comfortable and you would like to require more elaboration or so, you could do that. You could still do that by the end of today, because I'm going to make the recording of the review lecture tomorrow. You will have it before the Thursday exercise. So I will just take a look at by the end of today and try to incorporate your questions into a review lecture. It'll be rather short, not like 1 hour and 45 minutes, probably around about half an hour to 1 hour. Basically, that is a practice to show you how we're going to connect all the dots. And because that's the way I usually learn knowledge. And I hope you could also use it and finally get through the 6 weeks journey into one mind map or so. And you really got everything in your mind, not just for exam, but also for your future experience. And more importantly is some detailed deadlines. So the assignment for this week is open. Maybe you will learn more details about it tomorrow, but you probably have already seen it. It is not a usual assignment. It is basically kind of a rehearsal for you, really to help you about your review and about the final exam. So the deadline for assignment is the usual time, just to make a notice for those guys who had found many reasons to be late to submit your assignment. We were basically generous to allow you to do that, but for this one, you are not allowed to do that at all. So if you fail to submit on time, this assignment will be not counted, unfortunately. Because we're going to give you the answers right away. The solution will be given maybe half an hour or 1 hour later than the deadline of the assignment, because the solution is more important than you doing it. So if you use that to learn and to guide your review, it really helps you to get a good preparation for exam. And then you have the case study. No, don't forget about it. It's open. There are 2. So you will get 10 points extra. So use it to improve your grades. And the deadline is 6 p.m. the week after. And so not this Sunday, but the coming Sunday next week. And basically that means you have time after the exam, this exam and also the exam week. If you didn't do it before, because the case studies were open actually 3 weeks ago. So if you didn't do it before, try to catch it up to use it to improve your grade. And tomorrow is the final exercise. Try to be there, because they're going to be given lots of information about the exam and also some detailed Q&A if you have. Finally, a basic information about the exam.
Sorry. Is it tomorrow or on Thursday? On Thursday.
Oh, sorry, Thursday. Yeah.
Yeah.
So tomorrow is Wednesday, right?
Yeah.
Thursday.
Okay. Thanks.
It's the usual time. It's the usual time. Yeah. The exam is going to be next Tuesday. Yeah. So the time is defined. You know it. Details will be given on the exercise on Thursday, not tomorrow. Yeah. But details will be also given on my courses. So if you had a reason to miss the exercise on Thursday, and then pay extra attention on my courses, how to participate in the exam and how the exam rules are. So you will learn everything over there. When she made a very excellent preparation about the exam over there. Just gave you a basic information. We have 2 parts for exam, so maybe a little bit different from the exam you had for other subjects. So we have a written part and oral part. So the kind of weight for written is 70% and oral is 30. Little bit details about written is it's basically an open book exam, so you don't need to close your materials or everything, because we're going to do it online. Basically, you could use anything you have, like Google, like exercises before, anything you could find. Because we're kind of training you to solve a problem. We're not trying to use exams to disqualify some people, right? So if you could use anything you have, resources to solve problems, that's good enough. What you could not do is communicate with your peers. So written exam or exam is completely individual. So we don't do that as team. Yeah. Our exam will be defined as groups. So basically we have something like 3 or 4 people, depending how many you're going to participate in the exam. 3 to 4 people into one group, and each group has around about 15 minutes to do the oral exam. So basically I will ask you questions during our exam. It will be very simple. It will be rather kind of informative, because I would like to use our exam to see the overall kind of message you've learned from this lecture and kind of the overall understanding you have achieved via this 6 weeks. Yeah, if you perform really good in our exam, I could tell you that will give you a benefit for your final for your final remark, because that is a kind of a overall reflection of what you learned during this course. All right, I think that would be all for the course. As I said, you would get more details during the exercise on Thursday. So if you still have any questions, you could really ask now. Stop sharing, right? And if you don't have any questions, I would really wish you good luck with the exam, good luck with your study, and good luck with your life. So we will still see you during exam, but I would wish you already here best wishes. Yeah. And maybe we will see each other in other occasions in the future.
Thank you.
Thank
Bye.
Everybody, enjoy. Bye-bye.
Hi, I have just a question.
Oh, sure. What is it?
Yes. Okay, I am the student with dyslexia. I think I talked with you, and I don't know if I need to send you again the papers or something like this, because normally I have more time for do my exams.
Oh, yeah. Now I remember. That is especially related to the written exam, isn't it?
Yeah.
How much time extra you usually need?
It's depend.
Yeah, I think you gave me some number before, right? You
Yeah,
need
I
something
think
like 50% more time or something like that.
yeah.
The written exam is having 2 hours for normal students. For your special case, so that means we could give you 3 hours to do it. Is it okay?
Yeah, it's okay.
All right. So we need to, I will discuss with Wenqi and Rongfei this evening or this afternoon, how we carry that out.
Okay.
Yeah, yeah. Because the whole exam will take 4 hours. You can finish your written exam while we're already conducting the oral exam for the other students, and you could finish it, and we will basically put you into the second group, not the second group, but the second kind of part of the oral exam. Okay,
Okay.
good.
Thank you.
All right, no problem.
Bye.
Do you still have more questions? No? All right. Good. Then see you, Rongfei and Wenqi. So in the afternoon, we will settle down the exams. Bye.
Bye.